So, last class we are discussing about the loop transfer recovery of a LQG problems. Then just if you recall this what we have done it, that LQR problem provides the excellent robust properties in the sense that gain margin is infinity and phase margin at least 60 degree. This is the robust property, is excellent robust property we obtain in simple LQR problem. But when you are designing the LQG problem, assuming that state equation and measurement equation is corrupted with noise and the noise statistics is known to us a priori, then in that situation, since the states we are estimating using a Kalman filter, in that situation loop transfer function is different from LQR loop transfer function, which in turn that robust properties of LQR is totally destroyed, in the sense that we are not able to obtain the gain margin to infinity and the phase margin is not at least 60 degree. So, in order to recover that what is called robust properties, we can we have adopted some technique which is called the process noise covariance matrix. We can split up into a two parts. So, if just we are just what is called recall our earlier procedure, the how to recover the what is called LTR, agree. So, how to recover phase and gain margin of LQR, and phase margin we know the 6 at least 60 degree in LQR and gain margin is infinity, but in case of LQG these properties is totally lost. So, how to recover that one? So, that can be recovered by selecting the process noise, that can be recovered by selecting the process noise covariance matrix that is gamma W gamma transpose into two parts that we have mentioned it W gamma W0 gamma transpose plus Q B into B transpose, where this is the initial guess of noise covariance matrix, initial guess of W, initial guess of W, this W and Q is a some positive scalar quantity. So, this we have split up into two parts and we have shown in the last class how we have what is called regain the loop transfer function, agree, as LQR problem. So, in this process if just following assumptions are made. First assumption is made that system is minimum phase systems, minimum phase system, and we also made another assumption that number of inputs, that means input matrix and output matrix, then another matrix is input matrix B and output matrix C have the full rank with number of inputs M is equal to number of outputs. This assumption we made it to derive, to modify the what is called loop transfer function of LQG. Using the matrix identity, that last class what we have derived, we have briefly we are summarizing that one. Using the matrix identity, two identities we have used it, then we have derived that linear quadratic regulator loop transfer function is same as the linear quadratic regulator loop transfer functions. We using this, that noise process noise covariance is split up into two parts, and we made the assumption that minimum phase systems and B and C have a full rank with MDs. With these assumptions and using the following matrix identity, following matrix identities. What is this matrix identity? We have used it, that is first matrix identity we have used it, that phi C of S is equal to loop transfer, that is closed loop transfer function is equal to S I minus A minus B k whole. So, this is a closed loop transfer function when there is no noise process noise in the state equation and measurement equation, when in other words when Kalman filter is not used. This is this matrix lemma, this equal to, we have written like this way, phi of S into I plus B k phi of S inverse. This matrix identity we have used it. So, where phi of S is equal to S I minus A whole inverse, that we have derived last class. This is one matrix identity we have used it. Another identity we have used it, that I plus B k phi of S whole inverse B is equal to B I plus k phi of S into B whole inverse. So, that is another matrix identity we have used. Using these two matrix identity, we finally derive the expression, we derived the expression, and last class if you recollect this one, that expression we got it. Limit q tends to infinity L r phi of S this into C phi of S B bracket I plus k phi S B bracket whole inverse. That bracket, another bracket is there which we missed last class, whole inverse. Agree? So, now you see this this, if you can see, this and this is identity matrix, because A into B into C whole inverse is equal to C inverse into B inverse into A inverse, provided A, B, C all inversion is exist. So, if you do this process, then ultimately you will can k phi S into that this B, then I plus k phi S B whole inverse, then this is I plus k phi S B this, then this whole inverse C phi S into B whole inverse, agree, into then C phi S into B. So, ultimately we are learned up with this identity matrix, this and this identity matrix. This inversion is exist with the assumption that B and C with a number of inputs and outputs are same. So, this inversion, so we are left with this one, and which is nothing but the loop transfer function of LQR, that is nothing but a LS, which is nothing but a loop transfer function of LQR. So, in short, if you are summarize, if you select the process noise into this form and made the assumption that system is minimum phase system, B and C have full rank with m is equal to n, and following identities are applied during the derivations, what we did it during the derivations of last class, then we finally end up with this expression, and which in turn we can write it this one, and this is nothing but the loop transfer function of LQR. So, which is indicates that we have regained the loop or robust properties of LQR by selecting the process noise into this manner, and where if you select like this way, we will get the gain margin is infinity and the phase margin at least 60 degree. So, this is called loop transfer recovery. So, now let us go in a new topics, which is we call dynamic programming of discrete time systems. Next is new topics is dynamic programming of or for discrete time system. So, let us call, and this dynamic programming is based on the principle of it is based on principle of optimality. What is principle of optimality? We will discuss. In other words, it is based on Bellman's principle of optimality. This. Let us see what is this. So, the optimal policy has the property with initial state and initial decision. So, optimal policy has the property with initial state and initial decision, that the remaining decision, that the remaining must constitute optimal cost, must constitute an optimal cost or policy. Let us explain this thing. Suppose we have a trajectory whose initial state is x of t0. At time t is equal to t0, state position is x of t0 here, and the final terminating state is x of tf. Agree? This one. That means, x of t0 is the, if you assume this the trajectory is the optimal trajectory starting from initial state x of t0 at time index t0, and it is terminating at time t is equal to tf, at t is equal to tf, it is terminating at t is equal to xf, and this is x0 at time 0 along this optimal trajectory. So, and there is another point is there here in intermediate point, let us call that is x t is equal to t m. T is equal to m, that trajectory is x m. So, that point at t is equal to t m time index, the state value is x m. Agree? So, assume x t m be an intermediate. This is an inter state or point on the optimal trajectory. And let the cost j star x t m of x t m be the this indicates the optimal is the be the optimal cost for traveling the state from this point to terminal point is the j star x t m, from where it is starting x t m, and what is the position at time t is equal to t m, x position is x t m. Is this j star indicates optimal cost transferring the state from this to final state or terminal state here. The cost is this, and it is generated by j star from where it is starting at time t is equal to t m, x what is the state position at x t m. This is the called optimal cost of the trajectory moving from the intermediate point x m to terminal point x f. Similarly, if we just note j star t 0 x t 0, what does it mean? This indicates that optimal cost transferring the state or moving the state from initial state x t 0 or x 0 at time t is equal to 0 to final terminating state x f at t is equal to t f. What is the optimal cost? And that is denoted by this symbol. Agree? So, with the knowledge of this symbol, then you can say this one, this is the intermediate point, or state. Then it then follows that the portion of, you see, from what is the optimal cost from intermediate point to terminating point, optimum cost is j star t m comma x of m. Agree? This is the case. So, that I am writing if, then it follows the optimal, that the portion of the optimal trajectory x t m to x t f is also optimal, because we have considered this along this curve transferring the state from this along this time from initial state to final terminating state, this path cost is optimal, and this intermediate point belongs to the what is called that our optimal path in this way. So, from here to here, what is the cost we obtain it, that is also should be optimal. Now, let us assume that this is not optimal and this path is the optimal, the dashed line. From this to this, if you proceed like this way, I am reaching the terminal point here, along this path is optimal. So, now what is the optimal cost is required, optimal cost in during this process, that from here to here what is the optimal cost plus from here to here what is the optimal cost is. This cost is different from this one. We told that this is the optimal, and which contradicts our initial assumptions. Initially we are telling along this line, if you move the state from initial state x of 0 to terminal state x f at t is equal to f, then we will get the optimal cost. Okay. So, this if you move from this to this and this to this, assuming that this path cost from terminal point intermediate point to the terminal point, this is the minimum or the what is called lesser cost compared to this, then the whole state, the state when we are transferring from x 0 to t f along this path and dotted path, this will be the optimal, but that contradicts our initial assumptions. Okay. So, which cannot be done, which cannot be possible. So, I am just writing these things once again. Assume that the dash curve or path represents a smaller cost than the solid path. Or if you just include this is A, B, C, this path is D, this path is A, E path, then this dash path would provide less expensive route or path from x t 0 to x t f. This contradicts our original, this contradicts the optimality of the original trajectory. Okay. So, this is the optimal path only. Now, this optimal control strategy is the optimal control. My question is that from here to here, it will move or travel from this point to the initial state, this to this, under the control action. If you think from control point of view, the states want to move from this point to this point, agree? And if you move along this line, that will be give you the optimal cost. And what should be the choice of control action, so that the state will move along this path. So, the optimal control trajectory, the optimal control trajectory or optimal control strategy or control law strategy can be obtained by backward pass from final stage using principle of optimality. This indicates that if you know the terminal cost of this one end point terminal, then backward you find out what is the cost is required from here to here, then from here to here. Backward pass, that means optimal control strategy can be obtained optimal control strategy and control law can be obtained backward pass from final stage to the final stage using the optimality principle. The decision, this is the thing, decision is nothing but a choice of alternative leaving path from a given node. Our decision, what is the decision, which path will move, this is nothing but a alternative leaving path from a given node. Okay. So, let us take an example and see how we can derive the principle of optimality based on principle of optimality to find the optimal control law U in case of discrete time systems. So, discrete time dynamic systems. So, this principle of optimality will apply in order to implement the control law based on the principle of optimality. So, let us call our discrete time model is given by that x k plus 1 is equal to f of k, x of k and u of k, and this dimension of this let us call number of states are n cross 1, number of inputs m cross 1, agree, and this number of states are n cross 1. And in general this is the function of x and time index k and u. Any discrete time system in state space form one can write it x k plus 1, k indicates the time index, which is a function of state and input and the time index. So, this function can be linear or can be nonlinear, linear or can be nonlinear. Agree? So, with our initial state x of t 0 is equal to x 0 and the corresponding performance index and the corresponding performance index P I performance index of the given system is given by j is equal to j 0 then phi n capital X of this plus summation of k 0 small k 0 to n minus 1, then it is a f k x k and u k. This capital F is the performance index, which is in generally may be quadratic form or any form. So, this is the our performance index is given. So, our job is to find a control law U in such a way, so that J is minimized, agree, and correspondingly optimal trajectory of the state we can obtain it. So, we are mentioning it that we are moving backward. So, terminal cost, final terminal cost we know, then we let us call x, this is the call terminal cost, and our terminal point t, that is k is equal to n, and nth time index is the terminal, because k is equal to n is the terminal time index. So, let j k, j suffix k star x of k of whole k. What this indicates? If you are considering the this indicates that we are moving the states at kth instant to final time index k is equal to n index. For that one, what is the minimum cost of this one? So, this we are writing is j, this is the minimum cost of transferring the system state from x, capital X of k at time index k to the terminal state x of n. So, this indicates from where we have started, kth instant the state is transferred to a final state. That indicates which instant the state is transferred, and corresponding to this instant state is x of k. We have transferred the state to a final state. If k is equal to 3 and n is equal to capital N is equal to 10, that means we are transferring the state x of 2, k is equal to a final state k is equal to k of 10, because capital N is 10. So, that corresponding cost we denoted by j star of 2 if k is equal to 2. So, this is the same definition what we have considered earlier, that what we are talking about this. So, what is j star of T m? The state at time t is equal to T m, we are transferring that state to a final state, agree, and what is the final state? That t is equal to T f. What is the cost is required? So, because x of n is the terminal cost or terminal x, this is not that cost, this is the terminal point, because x of t is the terminal point. We have the terminal cost or terminal cost j n star x of n. That means j n final state to final state, what is the cost? That is the cost of this one. By defining that way, that will be the terminal cost j n star, and whose values is what in this expression. If you see just now in this expression, if you see, that means n is equal to k is equal to n. You see what you are written, k is equal to, you see this n, k is equal to n, k is equal to n. So, j x of n, this value will be terminal cost is that much, because k is equal to n means n upper lower limit is n, upper limit n minus, this expression does not valid, only this term is left. So, the terminal cost is f phi n of x n. So, this is the terminal cost. Now, using principle of optimality cost for transferring the state from x n minus 1. So, our state was x n is here. Now, x n is a capital X n minus 1. So, what is the cost or transferring from this to this? So, that we are going to, that using the cost of transferring the state from x n to the terminal point x of n as what you can write it. So, j n minus 1 star of x n minus 1. So, this meaning is we are transferring the state at time index n minus or k is equal to n minus 1 to k is equal to n, mean final state, terminating state. For that one, what is our cost? We have to minimize that u, minimize u n minus 1, and what is our performance index? Phi, terminal cost is phi n of x n, this plus phi n minus 1 x n minus 1 u n minus 1. That one bracket close, this one. Now, see, this is the terminal cost. So, what is our n? K n minus 1 step to final step. So, final step cost is this one, that k is equal to n minus 1 to n minus 1. So, f k is n minus 1, k x of n minus 1, u of n minus 1, that is what we have written. So, now we have to minimize this one, and which is a function of u. So, we have to minimize this one. So, if you recall this is nothing but as according to our notation, this is nothing but a x of n, terminal cost. So, now this is from n minus 1 at time index to terminal time index, means n. Now, in general we can write, in general we can write j k x k of this star. That means, how will you read this one? We are transferring the state at k is equal to kth time index to a terminating time, a terminating state at k is equal to capital N, time index k is equal to n, which you can write it minimize u k. You see, when n minus 1, minimize that, because the information is only n minus 1. So, minimize this, then k 2, that is your kth state at k is equal to kth instant to a final terminal condition. Then what we can write it for this one? That will be a f k u x k, then u k, then what is required for this one? Because j k plus 1 star k plus 1 star x k plus 1. You followed this one. In this expression, I will write k is equal to k n minus 1. So, last term n minus 1 of this, because we are doing backward cost calculation, we are doing it, this one. So, this will be that, which I can write it minimum u of k f of k x k u k plus j k plus 1, then x k plus 1, what we can write it is nothing but a f of k x of k u of k. So, now you see u of k is a function of that f small x is a function of small f, mean dynamic equation is a function of u k. That means, I am writing into x k plus 1 into this form. So, this then you do the minimize that thing with respect to u k. So, this is the basic principle, that you calculate the what is called control strategy backward pass, and ultimately you find out the optimal trajectory of the dynamic systems. Agree? So, it is clear to you because I am finding out the optimal cost from kth instant to final terminal state, when the state is transformed from kth to kth time index, that means state value is x of k to final terminal time index k is equal to n, then what is the optimal cost. So, this is nothing but I am writing from this one, k is equal to k n minus 1. So, from kth instant, that last kth instant, that this k is equal to, I write it, and other terms I clubbed with this one, and which I have written into this form. So, let us take one example and see how we can use the principle of optimality to find the control law in case of dynamic discrete time systems. So, example. So, our problem is we have given a discrete time system whose dimension is first order difference equations. So, 4, so let us write it, since it is a first order small x, 4 x of k is equal to 6 u of k, and your initial condition is given, state is x of 0. So, this is the discrete time dynamic systems. Subject to our so this is a system, and minimize, not subject to, minimize the performing index. And what is the performing index? J or J0 from initial state to final state we has given. So, this is given to phi, in general expression I am writing first phi n x of n, this plus summation of k is equal to 0 to n minus 1, then your f k x of k, agree, then u of k. So, for this particular problem, this is given like x of 2 minus 20 whole square. So, what is our phi n x of n is this one, our phi n of x n is that one. What is our capital N? The capital N is 2 plus summation of half k is equal to 0 to n minus 1, n is 2, this is our n is 2. So, it is nothing but a 1, and which is nothing but a n minus 1 of f k, that f value is given, this expression is given, I am just writing here 2 small x k whole square plus then your 4 u k whole square bracket closed. So, the phi capital phi x n is given this one. So, our performing index is this one. Our problem is now find out u k. That means, I have to find out u k means 1 in order to get x 2 terminal state x 2, agree, that reach to the terminal state x 2, I have to find out u 0 and u 1 by applying our optimal control strategy, that this is our performing index. So, using PO, principle of optimality, find u of 0 and u of 1, assume no constraints on u of k, agree, no constant of it, you minimize that one. So, now What is unknown is here, you see I have to choose the control law u such that this performance index is minimized. Once you find out u 0, immediately you can find out x 1. Then once you know x 1, find out the optimal value of u 1, you will know x 1. So, if you move along this trajectory, the performance index will be minimized, this one. So, how to solve that problem? Solution. So, we start with backward pass. So, we have, if you recollect that J 2 star of x 2, what does it mean? Small x 2. This means what is the terminal cost is required, and our terminal cost is that one only. Because k is equal to 2, if you write k is equal to 2 here, instead of k is equal to 2, 1, that this expression does not valid. So, what you are writing for this one, this equal to our terminal x of 2 minus 20 whole square is equal our terminal cost. So, this. Next we can find out what is called j 1 of x, j 1 x of small x of 1 star. What does it mean? I know the terminal cost x, k is equal to 2, this is the terminal cost. Then I find out backward from x 2 to x 1. In other words, I come from x 1 to x 2, if what is the our cost is involved. That is nothing but a minimize u of 1, f of 1, x of 1, u of 1 plus j 2 star x of 2. Look at this expression. So, k is equal to 1, 1 to 1. So, it will be f of 1, x of 1, this, then this j phi of 2 or x of 2 is nothing but a terminal cost j of 2, this one. So, that is you minimize. So, now I will write expression m of u, u of 1. What is the expression for this one? We know already this expression is given that one. Agree? So, we will write it that half twice x of 1 square plus 4 u 1 of 1 square. So, that is our that quantity plus this quantity is that one x of 2 minus 20 whole square, that things. So, this is the terminal cost I have written, and this is for x is equal to 1, that 2 x of 1 square plus u y of 1 square I have written. Now, you differentiate this with respect to u, that will give you, if you differentiate with respect to this and u of 1, then half twice x 1 square plus 4 u square of 1, and this I can write in terms of x 1 and x 2. Then that is nothing but a, if you see this one, k is equal to 1, that means 2 x of 2 is equal to 4 x 1 minus 6 u 1. So, I can write it 4 x 1 plus 6, it is 6 minus, that is minus 6 u of 1 minus 20 whole square, that if you differentiate with respect to a. Then by principle of what is called how you differentiate this with respect to this, then we can write it. Note, no constraints, note, no constraints on u of 1. So, optimal u 1 is obtained, optimal u of 1 is function of x of 1. So, this if you do difference equation, that not difference equation, that optimal cost in discrete time domain, if you differentiate with respect to that 1, I mean u of 1, and that u of 1 you will get function of x 1 only. This is what we have written it here, and this is nothing but it is the optimization problems. It is the problem of optimizations, discrete optimizations. So, what we can learn? Del u of 1, then whole thing. What is this whole thing? That this half cancel this 2. So, I will write it x 1 square of 1 plus 2, that is 2 plus 2 u square of 1 plus 4 x of 1 minus 6 u of 1 minus 20 whole square whole bracket. So, if you differentiate with respect to 1, it will be 4 u 1, then u 1 is coming here. So, this will be twice, this will be a twice 4 x 1 minus 6 u of 1 minus 20 into minus 6 is equal to 0. This is equal to 0. So, if you solve this one, you will get the expression u of 1 is nothing but a 12 x 1 minus 60 divided by 19. This is equation 2. Agree? So, this x 1, now look at this one in basic equation of dynamic equation. K is equal to 0 means x 1, x of 0, y of 0. So, x 1 depends on u 0 and x 0. Note, x 1 depends on x 0 and u 0, which we do not know, only x is known, this is unknown. So, let us see how to do. So, we are now where we are now x 1. For x 1 to we want to shift from x 0 to x 1, what is the optimal cost required, optimal path, and that we have cost is j 1 star of x of 1. It indicates is what? The optimal cost transferring the state from x is equal to x 1 to x is equal to x 1 to x 2. What is the optimal cost? Because we know u 1 expression is that one. If you put this value in the expression, that half twice x 1 square plus 4 u of 1 square plus j 2 star of x of 2. If you put this one, then j 2 star is what we got it? Just now we have found out j 2 star. Say j 2 star of this is that one. So, you can write it that half twice x square of 1 plus 4 u 1 we know. What is u 1? 12 x 1 x of 1 minus 60 divided by 19, that square. So, that is I am writing for this part plus j 2 square, that one, that is 4 x 1 minus 6 u of 1 minus 20 whole square. and if you simplify that one, finally we will get it. If you simplify this one, we will get it finally that x 1 x of 1 square, then twice 12 x of 1 minus 60 divided by 19 whole square plus 4 x of 1 minus 20 by 19 whole square. The three parts x 1 square plus twice 12 x 1 minus 60 by 19 whole square plus that term. If you use the value of u 1 here, then 4 x 1 minus 20, then this one. So, this is the final expression. Let us call this expression is 3 and expression number is this is 1 and 2 we have considered that u 1 expression. What is u 1 expression? That is 2. So, so what is our next? Then we know the optimal cost up to backward in up to the state x of 1 state. Now, we are moving the state x of 0 to x of 1. What is the optimal cost of that one? So, j 1 star x of 1, this cost we have to find out. And how will you find out? You see that our basic expression for this one. Say now, this is k is equal to 0, n is equal to 2. So, k is equal to 0, n is equal to 2, n is equal to 1, k is equal to 0, f of 0, x of 0, u 0, then f of 1, x of 1, u 1. That cost we have calculated backward. So, our expression will be half minimum of u of 0, then half twice x of 0 square plus 4 u of 0 square, that one plus j 1 star of x of 1. What is j 1 star of the x 1? That optimal cost required to transferring the state of x of 1 means k is equal to 1 time index to x of 2. This is the time index, and now this is we have to find out minimum value of u, so that this what is the trajectory from x 0 to x 1, that we can find out this one. So, we will continue this thing in the next class. Okay.